Okay, so today we are going to be going through the Science 10 Section 1 review. So if you could have that handy or right beside you, that would be excellent. I'm going to be making my notes on the whiteboard. That is a screen on the Zoom. So if you could go ahead and pin that, that would be excellent. Okay, if you have any questions, feel free to ask as we go along. We are recording, so if you would prefer not to ask during the recording, just maybe write down your questions and save them for the end. Okay, so we'll just start right from the top here. So section 1, atoms, elements, and compounds. This was the kind of intro to chemistry. So reviewing the Wimmis symbols found on page 8 in your textbook. So just be familiar with these, right? Like know what an exploding bomb is, know what an environmental hazard, flammable, oxidizing agent, etc. Okay, I'm not going to draw all these out, but make sure you guys are able to identify these. If I give you one symbol, you guys need to be able to identify that. Okay, so those Wimmis symbols. So Wimmis stands for Workplace Hazardous Materials Information System. Okay, so that is Wimmis. And then the second one is MSDS. This is Material Safety Data Sheet. Okay, and what type of information will we find on these? Well, we are going to find how to handle the chemical, how to store the chemical, how to clean up the chemical, and how to dispose of the chemical. Also, how to treat somebody that may have ingested this chemical as well. Okay. Any questions there so far? Neat. Okay. So jumping forward, so matter, remember matter kind of makes up everything. That's why we cannot trust matter. I held up the fictitious laugh sign there. Yeah, so matter makes up everything. So we can kind of break down matter into a few subcategories itself. So for mixtures, these are just going to be like not pure substances essentially. So for example, like pop or orange juice or coffee. Okay, those are mixtures, not pure substances. We can break mixtures down into heterogeneous and homogeneous mixtures. So remember, homogeneous is same throughout, same concentration throughout. Okay, it's the same. And then hetero is different concentration throughout. So for example, if we had, I don't know, if we had like no pulp orange juice, it could be the same concentration throughout. But if it was like pulp orange juice, if there's different concentrations of pulp throughout that mixture, then it would be a heterogeneous mixture. Okay. So pop would be a great example of a homogeneous mixture. Okay, because we cannot see the individual parts within pop. Okay. And coffee, If you let your coffee sit for long enough, eventually some of the coffee grinds will precipitate to the bottom. So that would be another example of a heterogeneous mixture. Okay. Pure substances are just that. Okay, they're pure substances, and that can be broken down into either elements, so like sodium, hydrogen, oxygen. Okay, if we had like liquid sodium, if it was just like molten sodium metal, that would be a pure substance. And then we're gonna have mixtures, or sorry, compounds. Okay, and these are going to have like no impurities. So like a completely pure sample of water would be an example of a compound. Sodium chloride would be another example of a compound. Ammonia, okay, just to name a few. Okay, so jumping forward to question 5. So name 2 characteristics of each atom. And then we're going to draw a diagram. So Dalton, he was the first one. He has the solid sphere model. He thought atoms were they were not able to be broken up. They were just like a sphere. So atoms were atoms. Atoms of one element had different properties than another atom. Okay, so for example, if we had a sample of oxygen versus a sample of hydrogen, Dalton would have thought that those atoms would have similar properties, or different properties rather. Okay, all matter is made up of atoms, and atoms can combine to make substances. Okay, so that's Thomson, or that was Dalton rather. Thomson, this is the cookie model or the plum pudding. So we had lots of positives, but we also had kind of like negative chocolate chips throughout. He said atoms were made from smaller particles. Okay, and electrons were on the outside. Okay, moving down to Rutherford. So he kind of had his positive nucleus with the electrons kind of throughout. He had his gold foil, so this will be Rutherford. His gold foil experiment where he shot particles at a thin sheet of gold, and he noticed that some of those particles actually bounced back at him, but the majority of them made it through. So he realized that the atom was mostly empty space. Okay, and we have a positive core. Okay, lastly, we have Niels Bohr. He had his energy, so he has a positive nucleus as well. And he had electrons in particular orbitals. Okay, so remember, the first orbital will have only 2 electrons, and then each orbital going past that will have 8 electrons. So if this had 10 electrons, this element would be neon. Okay. Positive nucleus, and we also had electrons in energy levels. All right. So on to question 6. So describe the following subatomic particles and where are these particles found in the atom? Okay, so protons, neutrons, and electrons. Okay, so protons, neutrons, and electrons. These are positive. Neutrons are no charge. And electrons are negative. Okay, protons and neutrons are called nucleons. Nucleons. They make up the mass or the nucleus of the atom. So let's do this. Okay, so protons and neutrons will make up the inside of the atom, and then we will have electrons on the outside of our atom. Okay. Yeah, that's all I have to say about that one. So electrons are on the outside. Remember, electrons are involved in chemical reactions. And the valence electrons are particularly important for that. Okay, moving on. So question 7, we're going to draw electron dot diagrams. I'm not going to do them for all of them. I'll just do a couple just to make sure we're on the same page. Okay, so let's just start with phosphorus here. So phosphorus, it has a atomic mass number of 31. So let's just say it has 31 protons plus neutrons. It has a atomic number of 15. So we know that there are 15 protons. Okay, and a neutral atom of phosphorus will have an equal amount of protons and electrons. So we know there are 15 electrons here. Okay, so if we subtract our atomic number from the atomic molar mass, so 31 subtract 15, we will get 16 neutrons there. Okay, so this was the atomic molar mass. And this is the atomic mass number. Okay. So if we were drawing an electron dot diagram for this, so remember, we are only going to draw the valence electrons in electron dot diagrams. So phosphorus will be here because it is in, it has 15 electrons. I know that the energy levels go 2, 8, and then maybe I'll do that one first. So we have 15 protons, 16 neutrons, and then we have 2 electrons, we have 8 electrons, and then we have 5 electrons. So this would be the energy level diagram. And these guys up here. These guys up here. So this row is our valence electrons. So for our energy or electron dot diagram, we are only going to show the letter, and that is going to be representative of the the electrons that are not valence electrons, as well as the protons and the neutrons. So now we will just go ahead and add our 5 valence electrons. Okay, so that is for phosphorus. So let's do we'll do calcium next, and then the calcium ion as well, and then we will move on, okay? So calcium. So calcium has a atomic mass or atomic molar mass of 24. It has an atomic number of 20. Sorry, I don't know what I was looking at. 40. It has an atomic number of 20. So this will tell us our protons. And this tells us protons plus neutrons. So if I do 40 minus 20, if I subtract the atomic number from the atomic molar mass number, it will tell us the amount of neutrons we have. When it's just the calcium element, like not the ion, the amount of protons will equal the amount of electrons. So for calcium, we will have 20 electrons as well. So let's do calcium first. So calcium, we have 20 protons, we have 20 neutrons. And if we have 20 electrons, we'll have 2 in our first level, 8 in our second, there's 10. 8 in our third, there's 18, 8, 6, and then we'll have 2 electrons in our valence level. Okay, so that is for calcium. Now, if we wanted to do, okay, we'll do the dot diagram as well. So calcium itself has 2 valence electrons. Okay. Now we will do it for calcium cation, so plus 2. So remember, when it becomes positive, it is a cation because it's giving away its electrons. So remember, electrons are negative. So if you give away something that's negative, you're going to become more positive. Okay, so we'll have calcium plus 2. We're still going to have 20 protons, and we're still going to have 20 neutrons. Okay, we're still going to have our valence electrons too, or sorry, our inner electrons, but the valence electrons have been donated to something else. Okay, so when you're drawing this, these guys here will become our valence electrons. Okay, so for the calcium +2 electron dot diagram, we're going to have 8. Because remember, the valence electrons are the outermost electrons for an element. Okay? Cool. Okay. Question 8. Write a definition for the term isotope. So isotope, this will have the same number of protons. Remember, the amount of protons defines what that element is. Okay, so isotopes, we will have the same number of protons, but a different number of neutrons. Okay, so for example, we could have carbon 12, we could have carbon 13, and we could have carbon 14. Okay, these are 3 pretty common isotopes of carbon. So remember, this will tell us the amount of protons and neutrons. Carbon will always have 6 protons. Okay, so for carbon 12, so 12 will be the atomic molar mass. So if we subtract the amount of protons from the atomic molar mass, so 12 minus 6 equals 6 neutrons. Here, if we do 13 minus 6, we will have 7 neutrons. And 14 minus 6 will give us 8 neutrons. Okay, so those are isotopes, the same number of protons, but a different number of neutrons, okay? Okay, so a certain isotope has a mass number of 35. The isotope has 18 neutrons. Write the nuclear notation to represent this isotope. So remember, the mass number will tell us protons and neutrons. So if I subtract the neutrons from the mass number, it can tell us how many protons we have. So 35 minus 18 is equal to 17 protons. So let's jump to our periodic table here. I see that chlorine has 17 protons. Okay, so now to write nuclear notation, you're going to write the element symbol. You'll write how many protons are in the bottom left, and then the mass number at the top left. Okay, so this would be nuclear notation for chlorine. All right, so question 10. For each isotope, write the proper nuclear notation and indicate the number of subatomic particles that are present. So let's just do neon 22. So from the periodic table, I see that neon has an atomic number of 10. Which equals 10 protons. Okay, so if I subtract 10 from 22, so 22 subtract 10 will give me 12 neutrons. And if it's in neutral sample of neon, we can assume that the amount of electrons will equal the amount of protons. So then we'll have 10 electrons. And now we'll write proper nuclear notation. So it'll be Ne 10 and 22. Okay, I'll do one more for carbon 13. So atomic number of 6 always. So 6 protons. So 13 minus 6 is equal to 7 neutrons. And we can just assume that we have a equal number of protons and electrons, so 6 electrons. And then proper notation would be 6 and 13. Okay. I'm going to leave carbon 14 because it's very similar to carbon 13. That is how we do it. Okay. So on the periodic table, be able to identify the alkali metals. So that is the first group going down. So that'll be lithium, sodium, potassium, rubidium, cesium, and francium. Alkaline earth metals, that is beside it, one to the right. So beryllium, magnesium, calcium, strontium, barium. Our halogens are going to be fluorine, chlorine, bromine, iodine, acetane. And then last, there are noble gases: helium, neon, argon, krypton, and xenon. Okay, so we're getting there. So define and provide an example of each. So ionic compounds. Ionic compounds, these are going to have a complete transfer of electrons. Okay, so an example of that would be sodium chloride, my favorite example of that. Ionic bonds. These form between a metal and non-metal. Okay, so in this case, we have a metal and a non-metal. Okay, molecular compounds. This involves a sharing of electrons. Okay, and a covalent bond. This is this forms between two nonmetals. Okay, so a good example of this would be H2O. Okay, and lastly, write the chemical formulas for the molecular, so the diatomic and polyatomic elements. We talked about this briefly yesterday, but I'll just finish up here. So for our diatomic molecules, so di being 2, I'm just finding a periodic table here. So our diatomic molecules, we have hydrogen, And then we will have nitrogen. Oops, don't let me forget the subscript there. So we have hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Okay, those are our 7 diatomic molecules. Okay. Okay, and then we have some polyatomic molecules as well. So that's going to be our P4 and our, oops, and our S8, our sulfur 8. Okay, these are important. So you need to know these for when you are predicting the products of reactions. Okay. And predicting reactions will be, that's in section 3. Okay, so we will cross that bridge when we get there. But just make sure that you know what the diatomic molecules are and what the polyatomic molecules are. Okay, thank you for tuning in, and I'm going to stop the recording now.